Welcome to Brain Vision.
Okay, so now we're trying to show that the partials of the function given at the point 0, 0 exist, but the function itself is not differentiable at 0, 0. Okay, so let's write out our function. This is equal to xy over x squared plus y squared when xy is not equal to 0, 0 and 0 when xy is equal to 0, 0. Okay, so let's take the partial derivatives straight from the definition. So the partial derivative of f with respect to x at 0, 0, this is just a limit as delta x goes to 0, f at 0 plus delta x 0 minus f at 0, 0 over delta x, which gives limit delta x to 0 so this is 0, right? Just by substitution you can conclude that that this guy is 0 and minus f of 0, 0. This is given in this one, so this is 0 over delta x, which leads to 0. So partial derivative of f with respect to x, this is 0. And we can do these similar things with the partial derivative with respect to y. And this is f at 0, 0 plus delta y minus f of 0, 0 over delta y. And similarly, when we substitute 0 and 0 plus delta y into our function, this is the upper one, because x and y in that case is not equal to 0, 0. So we just substitute 0 and 0 plus delta y into this equation, and then we can find that to be 0 minus 0 over delta y, which is equal to 0. Okay, so now that we know that the partials do exist for both x and y for the function f, we just need to prove that the f is not differentiable at 0, 0. And we're going to do that by using the definition 7 in the textbook at the page 970. So if the function f is differentiable at 0, 0, then the function needs to satisfy the equation delta x plus fy 0, 0 delta y plus epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1, epsilon 2 approaches 0 as delta x, delta y approaches 0, 0. So we need to have the equation and the conditions stated below in order to conclude that the f is differentiable at the point 0, 0. So let's find the expression. Let's first find the expression of delta z in terms of the function f. So delta z at the point 0, 0, that is just equal to f at 0 plus delta x, 0 plus delta y minus f 0, 0, which is just equal to delta x, delta y minus f at 0, 0. Okay? So when we substitute delta x and delta y into our function, we have delta x times delta y over delta x squared plus delta y squared, and f at 0, 0, this is given in the lower part of the of our function, so that's just 0. So now we have delta z is equal to delta x times delta y over delta x squared plus delta y squared. And as I said, in order for a function f to be differentiable at the point 0, 0, we need to have the epsilon 1 and epsilon 2 that goes to 0 as delta x and delta y approach 0, 0. And also we also need to have that then the limit delta x, delta y as it approaches 0, 0, delta x, no, excuse me, this is delta z, this also needs to approach 0, because when you look at the expression, we have this is just constant times delta x that approaches 0, and constant times delta y that approaches 0, and if a function is differentiable at 0, 0, this condition also needs to satisfy. So that means that if a function is differentiable, then delta z, as we take the limit of delta z, delta x, delta y approach 0, 0, the expression of delta z must also approach 0, 0. Okay, so let's find it otherwise, which means to prove that the limit delta x, delta y as it approaches 0, 0 of delta z is either does not exist or is not equal to 0. So let's show that is the case, and then we can conclude that the function f is not differentiable at the point 0, 0. And we found the explicit expression of delta z from just by substituting the delta x and delta y, and we found that to be this. Okay, so now we can find, we need to show that this does not exist, or is not equal to what is not equal to 0. Okay, so delta x, delta y over delta x squared plus delta y squared. Okay, and as we do in the usual limit, we can take a path, two different paths, and if we can show that the these limits with the different path leads to different value, then we can conclude that the limit does not exist. So let's take the path first as delta x equals delta y. That implies that the limit as delta y approach 0 delta y squared over 2 delta y squared is equal to 1 over 2. And then next path I'm going to take is delta x equals negative delta y. That means that the limit as delta y approaches 0, negative delta y squared over 2 times delta y squared, which equals negative 2 and negative 1 over 2. Now obviously these two does not equal to each other, so we can conclude that the f is not differentiable at 0, 0, because if it was, the expression, this has to be true, right? So now we did A, so let's move on to B. We need to explain why f sub x and f sub y are not continuous at 0, 0. Now, I'm gonna first do why f sub x is not continuous at 0, 0. As we found in A, we have f sub x at 0, 0. This is equal to 0. Okay, so, and I'm gonna take the derivative with respect to x of the of this guy, and then find the whole expression of f sub x, and then explain why f sub x is not continuous at 0, 0. So f sub x, xy, now that is equal to, I am going to take the partial derivative with respect to x of the upper function. So that is y over x squared plus y squared minus 2 times x squared y over x squared plus y squared, when xy is not equal to 0, 0, and then 0 xy when xy is equal to 0, 0. Okay, so we can just take the limit as xy goes to 0, 0 of the function. I'm gonna name it g of xy, g of xy, and see if that leads to 0, and otherwise we can conclude that f sub x is not continuous at 0, 0. Okay, so let's simplify g of xy. We can write this as y to the third minus x squared times y over x squared plus y squared squared. Okay, so now I'm gonna take the path x equals square root y, and then the function becomes square root y equals to y to the third minus y squared over y plus y squared over y plus y squared to x, to 2, and then we can simplify this to y squared times y minus 1 over y squared times y plus 1 squared, which is y minus 1 over 1 plus y squared. Okay, so I am going to take the limit of the g of xy. No, we just took the path x equal to square root y, so we just need y approach 0 of y minus 1 over 1 plus y is to 2. Now that equals to negative 1. So now we can conclude that the f sub x, partial derivative of f with respect to x, this is not continuous at 0, 0, right? Because the as given, we have when xy equal to 0, 0, f sub x is defined as 0, but when we take the limit of the upper function g of xy as xy approaches 0, 0, that does not approach 0. That for a certain path, this approaches negative 1, and the so that value is not equal to each other. And the similar thing for f sub y, because we have the exact same structure as f sub x time f sub x of xy when we take the partial derivative of f with respect to y, because the upper function is equal to xy and x squared plus y squared, and we just need to switch y and x in g of xy, and then you get f the upper function of the f sub y of xy. And then the same thing, we found that the partial derivative of f with respect to y at 0, 0, this is 0, and then we can do the exact same thing, right? But just replace x with y and y with x, and then take the limit as xy approaches 0, 0, 0, and then you can find the value to be different. So that's how you show that the partial derivative of f with respect to x and with respect to y, they are not continuous at the 0, 0.